Io shouldn't exist the way it does. It's a moon, and yet it's the most volcanically violent place in the entire solar system. Right now, as you watch this, 7 separate volcanoes are actively erupting on its surface simultaneously. One of them is pumping out 33 gigawatts of energy per micron of light. Scientists just mapped all of this, using the James Webb Space Telescope and an artificial eye made of neural networks. What they found didn't just surprise them, it forced them to rethink how planets are born. Here's the thing about Io that most people don't realize. When Galileo first spotted it back in 1610, it was just a dot. One of 4 large moons circling Jupiter. For centuries, it sat there in the textbooks, a footnote. A small rocky world, a little bigger than our moon, orbiting a gas giant. Nothing special. Then in March of 1979, Voyager 1 flew past it. And everything changed. Scientists watching the data come in saw something that stopped them cold. 9 active volcanoes erupting, shooting fountains of material hundreds of miles into space. On a moon, nobody expected that. Nobody had predicted it. The models said Io should be cold and dead, like our own moon. It wasn't. And here's where it gets interesting, because that discovery didn't answer the big question. It opened one. Why is Io doing this? What is powering it? The answer, when scientists finally worked it out, is something that sounds almost mechanical. Jupiter, the largest planet in our solar system, is pulling on Io with a gravitational force so intense that it physically squeezes the moon's interior. Like squeezing a stress ball, over and over, billions of times. That squeezing generates friction. That friction generates heat. And that heat melts rock deep inside Io and feeds those volcanoes continuously. The technical term is tidal heating, but what it really means is this. Io is being cooked alive by Jupiter's gravity every single day for 4.5 billion years. And it's not just Jupiter doing the squeezing. 2 of Jupiter's other moons, Europa and Ganymede, are locked in a gravitational rhythm with Io that keeps its orbit slightly elliptical. That slight wobble is what keeps the tidal forces locked in. It's a trap Io can never escape. Now, here's what scientists didn't see coming. For a long time, researchers assumed Io's volcanism was a relatively recent development. Maybe it ramped up over time. Maybe conditions changed. They were wrong. In 2024, a team from Caltech, led by Catherine DeClear, did something clever. They pointed a massive radio telescope array in Chile, called ALMA, at Io's atmosphere and measured the sulfur gases coming off it. Not just how much sulfur, but which kind. Here's the science in plain terms. Sulfur comes in different weights, different isotopes. The lighter version, sulfur 32, floats up into the atmosphere more easily and gets blasted away by Jupiter's radiation. The heavier version, sulfur 34, sticks around longer. What DeClear's team found was that Io has more of the heavy sulfur, sulfur 34, than any other object ever measured in the solar system. More than Earth, more than Mars, more than any asteroid or comet we've ever sampled. That ratio tells a story. It means Io has been losing the lighter sulfur at an enormous rate for an enormous amount of time. The geochemical modeling showed that in the past, Io may have been losing sulfur at 5 times the rate it does today. 5 times. That means Io wasn't always this volcanic. It was more volcanic. Possibly far more violent in its early history than anything we see on its surface today. Think about what that means. the most volcanically active world in the solar system, right now, today, is actually the calmed down version. And yet, even in this quieter state, it's doing things that scientists are still struggling to explain. Because here's what nobody could figure out until very recently. What's actually happening inside Io. For decades, scientists debated what Io looks like beneath the surface. The leading theory was straightforward. All that tidal heating had to go somewhere. The logical conclusion was that Io had a global magma ocean, a planet-wide layer of liquid rock sitting just beneath the crust, feeding all those volcanoes from one giant underground reservoir. It made sense on paper. Then Juno spacecraft started making close flybys of Io, and the data it sent back didn't match the theory. Juno measured Io's gravitational field with extraordinary precision, tracking how the moon's gravity tugged on the spacecraft as it flew past. That gravitational signature tells you what's inside. And what it told scientists was this: Io does not have a global magma ocean. Instead, it has individual magma chambers. Separate pockets of molten rock feeding separate volcanoes, like a network of underground furnaces rather than one giant lake of lava. According to Ryan Park, the lead author of the Juno study, this discovery does more than just correct our picture of Io. It changes how we think about tidal heating across the entire solar system, including moons like Europa and Enceladus, which scientists believe may have liquid water oceans beneath their icy surfaces. If tidal forces don't always create global magma oceans, then the internal structures of those moons may be far more complex than our models assume. In other words, what we learn about Io's guts directly affects how we search for life elsewhere. But here's the part that really got scientists' attention. Even with all of this, the Juno flybys, the ALMA data, the decades of ground-based observation, nobody had ever actually seen Io's individual volcanoes clearly from space. Not until a team pointed the James Webb Space Telescope at it and did something nobody had tried before. On August 1st, 2022, the James Webb Space Telescope turned its infrared eye toward Io. But the team, led by Joel Sanchez Bermudez at Mexico's National Autonomous University, didn't use Webb the normal way. They covered most of the mirror with a metal plate punched through with just 7 holes, 7 small openings, each acting as a separate light collector. This technique is called aperture masking interferometry. The beams of light coming through each hole interfere with each other on the detector, creating patterns that carry far more spatial information than a standard image. It effectively doubled Webb's resolution on Io, letting scientists see detail that would otherwise be impossible. But there was another problem. Io is bright, extremely bright in infrared. Standard image reconstruction software couldn't handle it. The math broke down because Io was nearly as large as the instrument's field of view. So the team turned to neural networks. They trained artificial intelligence on thousands of simulated volcanic scenes, then used it to reconstruct the actual images from the raw data. An artificial eye built to see what human-designed software couldn't. What came back across 5 separate exposures, taken within a single hour, was a mapped volcanic landscape. 7 active eruption sites clearly separated, the brightest one sitting just northeast of a volcanic depression called Seth Patera, pumping out roughly 33 gigawatts of energy per micron. 6 others clustered between 11 and 30 gigawatts, and surrounding several of the eruptions, broader glowing regions, possibly sulfur dioxide gas freezing back onto the surface as it falls back down. They even tracked the brightest eruption moving across the disk as Io rotated. Its measured speed about 190 miles per hour, matching almost exactly what Io's own rotation would predict. The map was real. The volcanoes were confirmed, and the cross-check came from the Keck 2 telescope in Hawaii, which had observed the same hotspots a month before and a month after, matching the Webb data almost perfectly. But here's what all of this adds up to. Io is not just a curiosity, it's a laboratory. The only place in the solar system where we can watch tidal heating in real time at full intensity on a world we can actually observe in detail. Every piece of data we pull from Io, the sulfur isotopes, the magma chamber structure, the mapped eruptions, feeds directly into our models for other worlds. Worlds like Europa, where a liquid water ocean sits beneath miles of ice, kept warm by the same tidal forces that are tearing Io apart. Worlds like Enceladus at Saturn, shooting water vapor into space from cracks in its surface. If life exists anywhere else in our solar system, the most likely candidates are those tidally heated ocean worlds. And our ability to find it, to understand what conditions exist beneath that ice, depends on how well we understand the engine driving it all. That engine is tidal heating, and the best place to study it is Io, a moon that shouldn't be as violent as it is. That was even more violent in the past. That has no global magma ocean, just a network of underground chambers we're only beginning to map, that we just saw, clearly, for the first time, through an artificial eye attached to the most powerful space telescope ever built. Scientists aren't afraid of Io because it's dangerous. They're afraid of it because every time they look closer, it tells them how much they still don't understand. And here's what I didn't tell you at the start of this video. Everything we just covered, the Webb observations, the Juno flybys, the sulfur isotope data, that's all about Io itself. We haven't even touched on what Io's volcanic activity is doing to Jupiter's magnetic field, or what it means for the future missions NASA is planning to Europa. That's a whole other story. And it's one worth telling. If you want that video, hit subscribe so you don't miss it. Drop a comment below. What surprised you most? The artificial eye? The magma chambers? Or the fact that Io used to be even more violent than it is today?